Hey guys, I'm Sranee and this is Lab 2, Motion of a Falling Object. The goal of this lab is to explore the motion of a falling object. For this lab, I used a crumpled up ball of paper and threw it onto the ground and observed it fall and recorded it. I then uploaded the video onto Tracker to track the position of the object over time, then constructed two computational models and compared both the computational models and the experimental data. Like the previous lab, the fundamental principle used in Lab 2 is also Newton's second law, or the momentum principle, which states force equals mass times acceleration and final velocity equals initial velocity plus F net over mass times delta t. We also need the equations for weight force and drag force. Both the equations are on the screen. B in the drag force equation is a proportionality constant. We need drag force and weight force because in this lab, instead of looking at constant velocity, like the previous lab, we were looking at changing velocity, which means we have a F net that is not zero. This means something in the environment is exerting an uneven force on the object, which is resulting in a change in velocity. In this lab, it is weight force, which is caused by gravity, and drag force, which is caused by air, which is in the opposite direction of gravity. This can be seen in the free body diagram here. So next, I uploaded the video of my crumpled up paper falling onto Tracker. I had to use the calibration stick to measure the diameter of the paper, and I also had to set the origin. As the video played, frame by frame, I had to set points to track its position. And based on this, on the right, a graph and a table is created. As you can see, the table is curved downwards in the negative direction, but is speeding up. Now we can take this data and compare it to our computational models. So in our computational model, there were several things that we had to change. So I initially added the paper's mass, then set the gravitational force to 9.8. I added the unit vector. I calculated the proportionality constant for drag force, which is the B in the drag force equation, which I got 0.003. This equation was calculated by plugging into the drag force equation and guessing and checking to see what best fits our model. I then, most importantly, added the equations for drag force, weight force, and F net. We need to build two models on GlowScript, one to stimulate the drop without drag and one to stimulate the drop with drag. For the computational model with just weight force, I just commented out the drag force part of the equation in the F net equation and ran the code. This is a resulting graph. We can then compare it to the graph with drag force. Side by side, you can see the two graphs with just the weight force and one with weight force and drag force. You can clearly see with just the weight force, the graph force is slowing down at a greater rate. So now we have both our computational models and our experimental models. We can put these into Excel, plot the data, and then compare. This is our final graph with both the observed positions and the predicted positions. So our observed position is orange, the red is the predicted with drag, and blue is predicted without drag. Then let's look at our computational models with and without drag. The model with drag is closer to our experimental model. This is because it accounts for the drag/air resistance which occurs in real life when you drop a piece of paper. The model without drag is decreasing faster because it's not accounting for that air resistance. The change in velocity is 9.8 meters per second, which is a force of gravity. The model with drag is more accurate representation of a real-life model. The errors between the observed position and the predicted position with drag could be due to experimental errors such as not tracking correctly, or things like breeze from the AC or the wind and things like that, or the paper not falling straight. So lab questions. The object dropped from rest will increase its speed until it reaches terminal velocity. So when the speed of the moving object is no longer increasing or decreasing and the acceleration is zero. The model with both weight force and drag force predicts this better. The model reaches terminal velocity at a point where grav force and drag force are equivalent. The graph was initially curved due to gravity, then straightens out to be linear due to constant velocity and zero acceleration. This is when terminal velocity is reached. Question 2. Changing the initial velocity does not change the terminal velocity, but it will reach it much quicker because throwing it downward will make it start at an increased velocity that is closer to terminal velocity. So in conclusion, it is clear that the drag force had an effect on the system and better represents a real-life model. And it is important to include all the accounting forces acting on a system when trying to find that force. Thank you.